And now we will go to the second topic in this subtopic. The second part of the video for this subtopic, that is a supervised classification. All right, in supervised classification, as we know, as what I explained in the previous video, um, supervised classification, they have a user intervention. That is, user have to give input, okay, through training sites. So what is basically a training site? Okay, so for training sites, an analyst must select the areas which represent a land cover classes of interest. Right. So the area selected to serve as a training site should be relatively homogeneous and extensive enough to provide good statistics. So when you select select the training site for the classification, basically you have to make sure that the area that is being selected is a homogeneous. It could not be a area of of this what we call it, mixture of different land covers or land uses, okay, such as the areas that have plantation and also the forest, so you mix together. No, you cannot do that. It must be, if it's forest, it would be only forest, only forested areas. It is plantation, it must be plantation. Urban must be urban. Water will be water. We have to very precise about this because it will affect the signature that being collected or recorded. So rule of thumb for number of bands, for and collect at least 10 times of number of pixels of the bands pixels per class. Means to say, the image that the training site that the area of the region of the training site that we use is not necessary to cover a bigger area. It can be only such a small areas, less than 100 pixel values for every training site, but the number of site must be higher. So you must have, let's say you create you do the for the forest. All right, training site for the forest. So it is okay to get a small chunk of the image, small part, bits of the image for the training site. But if possible, make the site make the number of the site, okay, many as possible and evenly distributed. Okay. Training site data can be collected by gathering in situ data or locate some sample plots with GPS on maps and the photos. Okay, so this is the first one where we capture the data, raw data, and after that we do the on-screen selections of areas of interest. This is where we will do during the lab, or using the on-screen seeding through the region graph if you have multiple images. So training site selection here. Okay, what does it mean by training site? Is this one, the square homogeneous, square homogeneous, this square homogeneous, and another one small but homogeneous. Bigger because it is a homogeneous area, should be okay. And this one, another one here, smaller part, okay. And also here, small part. If you aware that all of these classes, they have at least 2 training sites. Not necessary to get one big chunk of the area, but just a bits only, as long as it is homogeneous, it doesn't intrude to the other areas. Okay, and if possible, even the fairly distributed, some cover at the upper side, left, right, lower side, and so on. Okay, so this is how we do a training site, but of course this is quite small. We have to do more and more. So in supervised classification, there are some algorithms. Okay, so what does it mean by algorithms? Is a decision rule. So decision rule is a logical expression that guides the process. So this is just like how the computer think. Okay, the logic of how computer think. So the purpose is to place the unclassified pixels into the most likely classes. There are 3 common rules which are associated with the supervised classification, such as minimum distance, parallel pipette, and maximum likelihood. Okay, so this is how we identify or how we study the algorithm through two spectral bands displayed on the scatter plot. So here, if you look here, each letter will represent, okay, different kind of pixel value from selected training sites. So for band 3 versus band 4, this is how the pixel value, and this is how the scattering of those two values represent different kind of classes. As you see here, this is the group of the pixel value represents different classes. Okay, we have corn, sand, urban, hay, and also forest. Okay, so for all of this, suppose that there are some pixel value here, on here, but it still remains unclassified because this is what we do for our training site. All of this identified, this is our training site. For the first classification algorithm, which is a minimum distance, the computer will calculate, let's say this is the unknown pixel that we want to classify. Okay, so the computer calculates a mean vector. So this one, what are the mean? 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 And this one are the mean for this from the center of each determined or each identified classes. So we, after calculate the distance between the unknown pixel and each mean class, then the computer will assign to the closest to the lowest mean. So in this case, the unknown pixel, because it is very close to the corn class, so we classify it as a corn. So what are the pros and cons? Pro is simple to use, fast computation, no extensive training data needed, and easy to explain. And the cons, while this approach is computationally efficient, it is somehow insensitive with a different degrees of the variance. Okay, because the classes that we classify, it could be from other classes, but because of the pixel value is near to each other, especially for the features that are almost similar, so the sensitivity is quite low, so it will simply group the unknown pixel to the classes that it might be wrong. However, for the number 2 parallel pipette classification, okay, we have two unknown pixel here, number 1 and number 2. So for this parallel pipette, the computer will calculate, okay, decision regions based upon the mean of standard deviation for each classes, where it becomes a group of the standard deviation. So it gives you some range, right? Using the SD, it gives you some range. So the computer then examines the position unknown, and after that, whatever pixels that falls within the range from the standard deviation, Pipette will automatically assign it to that classes. So if you see here, number 1, before if we use the minimum distance, it falls into the corn. However, for Pipette, the number 1 unknown pixel falls into hay. For number 2, although it's quite almost similar, the distance from urban and sand. However, because it falls within the range of the urban, so it will be assigned as a urban. So per pipette, basically, we are using some metrics. Okay, so digital numbers for training pixels are formed into a mean vector for each classes, and standard deviation is calculated. And the limitations: if the unknown pixel is not within any classes boundaries, it will remain unclassified. So we look back again. If the pixel is here, it doesn't fall into any classes, so it will unclassified. Okay, unclassified. Okay, So, and it's quite sensitive to class variant, but insensitive to the class covariant, where we have the region overlap. Okay, for example, here the pixel number 1 that we have here, it, for the first one, it could be false on con, it could be true, but because of the overlap here, this region, okay, so it might fall into the latter part, which is A. So therefore, pixels are assigned to the last class tested. So it goes through the sequence of the classes, and given that A will be the later one, so the unknown pixel will be assigned to the later classes that with that being being analyzed. It's not the first one. All right, and then we have this maximum likelihood.